Okay, now that we've talked about the different categories of reactions you'll see and how to derive net ionic equations, let's start looking at the reaction categories in more detail, starting with precipitation reactions. Now, to be able to cover precipitation reactions, we need to go over what are referred to as the solubility rules. And these are a set of rules that allow you to predict, based on the formula of an ionic compound, whether it's going to be soluble in water or not. In other words, if it will dissolve in water or if it's incapable of dissolving in water. So some of the major rules are listed on this slide here. So for instance, some of the most consistent rules are that if you have an alkali metal cation or an ammonium cation as the cation of the formula of your ionic compound, that compound is going to be soluble. And as far as we're concerned, there's not going to be any exceptions to that. So if you're asked if a compound is soluble and it has any of these cations in the formula, you can immediately know that it should be soluble or capable of dissolving in water. It's never going to be insoluble. Secondary to that, there are other trends. So for instance, compounds that contain halide anions, so chloride, bromide, or iodide. We're not going to talk about fluoride, but any of these more three common halide or halogen-based anions are going to also be soluble with a few exceptions. So for instance, silver chloride, silver bromide, or silver iodide, AgCl, AgBr, or AgI, are insoluble, so they're an exception to this trend with halides. And mercury 1 and lead 2 plus compounds of these ions are also insoluble, but those are the only real main exceptions to that. Other trends with ions include all nitrates, all perchlorates, all acetates, and most sulfates are going to be soluble. So any formula that has any of these first three ions, nitrate, perchlorate, or acetate, you can assume, at least as far as this class is concerned, that any such compounds will be soluble with no exceptions. Now, most sulfates are soluble as well, but there are some important exceptions to that one. So some of these are similar to the exceptions with halides. So you can see mercury 1 and lead 2 plus cations are going to form insoluble sulfates. And then there's also strontium and barium sulfate are insoluble as well. For a more comprehensive look, we can look at table 4.2 here, and this will show us which cations and anions are generally found in soluble or insoluble compounds. If there's a general trend, what the exceptions to that are. So again, we can see our cations based on ammonium or alkali metals are all soluble with no exceptions. Our halogen or halide based anions are mostly soluble except for the exceptions mentioned earlier. Nitrate, perchlorates, and acetates are all soluble no matter what. And most sulfates are soluble with these exceptions here, which I pointed out to you earlier. Now, one of the probably best ways to use this chart is actually to look at the anion of a compound if you're trying to determine if it's soluble or not. The reason why we'd focus on an anion to help us determine if a compound is soluble or not is that the types of compounds that are generally insoluble are all generally insoluble based on their anion. So you can see compounds that contain carbonates, sulfides, phosphates, or hydroxides as their anions are generally insoluble. And there are some exceptions to these, but some of these exceptions are pretty predictable. So for instance, all of these have exceptions for group 1A cations, so alkali metal cations, and ammonium ions. And this is all related to the fact that any of those compounds with those cations will be soluble no matter what, as far as we're concerned. And those are the only exceptions for carbonates or phosphates. For sulfides and hydroxides, there are a few exceptions, but those exceptions are actually just the alkaline earth metals that form strong bases with hydroxide ions. So remember how I told you calcium hydroxide, strontium hydroxide, and barium hydroxide were all strong bases? If you can remember that, that helps with remembering some of these solubility rules as well. So those cations show up here as the exceptions to the generally insoluble trend of sulfides and hydroxides. If you don't have one of these four anions, then you're probably going to have a soluble compound, and the only kind of exceptions further along the line there would be with your sulfates here and your halides here for these two things here. So I think that's the simplest way to remember if something is soluble or not, although since all of your exams are going to be open note, you don't necessarily have to memorize this chart, although at least knowing most of it would probably be really helpful, considering that if you know something without having to look it up, then it'll save time, and if you're doing a lot of these problems anyway, like you should be, then you'll probably end up memorizing a lot of these trends by accident. Okay, so let's look at an example where we have a combination of two aqueous solutions and we want to determine what the molecular, ionic, and net ionic equations are for the precipitation reaction that occurs. And for this, we're going to need everything that we talked about with net ionic equations and the solubility rules. So let's say we combine aqueous solutions of silver nitrate and sodium carbonate. What reaction is involved? So one question you actually have to ask yourself to begin with is a precipitation reaction even going to occur at all? So you can imagine, based on the solubility rules, that if you combine two soluble ionic compounds, it's possible that the cation and anion combinations you get by combining those are not going to result in any compounds that would be insoluble. There are plenty of situations where that would occur. If that happens, there's not going to be a chemical reaction that takes place, because no insoluble compound will be formed to form a precipitate. However, let's say you were doing this reaction in the lab, and you combined aqueous solutions of these two soluble salts, and you got a chemical reaction that looks like this, where clearly we formed a white solid in this test tube. So that's good experimental evidence that a precipitation reaction has occurred, which means that we're going to form some insoluble compound here. So what we need to do is write down the chemical formulas of the products, and I really have to emphasize that we need to use the correct rules for forming ionic compounds from ions with known charges. So for instance, here's our silver nitrate, here's our sodium carbonate. Remember, sodium is +1 and carbonate's 2-, so we need 2 sodiums for every 1 carbonate. And then we need to write the chemical formulas for the products. Now, how do we determine what the products are? And for this, essentially what we're going to do is we're going to swap how the cations and anions are paired. All ionic compounds consist of cations and anions, so we're not going to combine a cation with a cation or an anion with an anion, but for instance, in our reactants, silver is combined with nitrate. So what we can do is we can combine our silver cations with the other anion from the other reactant, so carbonate ions, and then we can do the same thing with the other ions. So instead of sodium cations being paired with carbonates, we can pair them with the nitrates that started off going along with the silver. And so we get now silver carbonate and sodium nitrate. And one of the most common mistakes people make when doing this first step is to look at the chemical formulas of the reactants and assume automatically that you're going to have the same number of each cation and anion on the left as you do on the right. And the reason that's not the case is we haven't balanced this reaction yet. What we need to do is come up with the proper chemical formulas first, and then later balance the reaction. Again, it's just a super common and easily avoidable mistake to not do that and just try to jump immediately to balancing this. So silver is always Ag+, so we need 2 of those to balance the charge on 1 carbonate. Likewise, sodium is +1, nitrate is -1, so the correct chemical formula for sodium nitrate is going to be 1 sodium and 1 nitrate ion. So our formulas are Ag2CO3 and NaNO3. Now, only after we've come up with those correct formulas are we going to worry about balancing the equation. So we can see that we have 2 silvers in the formula for silver carbonate, but only 1 in silver nitrate, so we're probably going to need a 2 in front of AgNO3. And once we've done that, we also have 2 nitrates, and we have 2 sodiums in the sodium carbonate. So for sodium nitrate, we're going to end up with 2 of those. And at this point, we have the correct number of silvers, sodiums, nitrogens, carbons, and oxygens on both sides. So again, we balance the equation second after coming up with the correct formulas for our ionic compounds. Now that we have a balanced equation, we can worry about states of matter. So our 2 reactants are aqueous, and that's pretty much always going to be the case, because in order to form an insoluble compound in a chemical reaction, we would need to start off with soluble compounds. Now, those are both soluble, and you can confirm that with the solubility rules. Now we need to look at the identities of our products, which are sodium nitrate and silver carbonate. Sodium nitrate contains sodium ions and nitrate ions, and both of those things on their own automatically lead to soluble compounds. So based on either of those ions, we should predict that this will be an aqueous rather than a solid compound, because that's going to be able to dissolve in water very well, either on the basis of having sodium or having nitrate, but especially if it has both of them. Now, if we look at silver carbonate, this one's a little bit more interesting. Carbonate, CO3 2-, is one of those ions where most of the compounds that contain carbonate ions are insoluble. Now, there are some exceptions to that, but in the case of carbonate, those exceptions are just the alkali metals and ammonium cations. So silver is not one of the exceptions to carbonates being generally insoluble, and so silver carbonate should be insoluble, and hence it's going to be a solid formed in this reaction. And so the precipitate we saw in that test tube, that white solid, is going to be silver carbonate, Ag2CO3. And so when we balance this equation, our 2 reactants are aqueous, the soluble compound we form is aqueous, and the insoluble is going to be a solid. And the solubility rules determine whether something is an aqueous or a solid in all cases. Now that we have a balanced molecular equation with the states of matter, and those are important here, we're going to use those states of matter to help us decide, as we turn this from a molecular equation into a net ionic equation, which reactants and products should be dissociated and which ones should not be. So again, our 2 reactants are aqueous, and since they're aqueous and ionic, that means they're going to be strong electrolytes. Also, sodium nitrate is aqueous and composed of sodium and nitrate ions, so that will also be dissociated. So everything gets dissociated except for our insoluble compound, because remember, all of those ions are combined together in that solid. They're not dissolved and dissociated into the water. Once you dissociate everything in the ionic equation, we can go ahead and look for our spectator ions, which in this case are going to be sodium and nitrate. There's 2 dissociated sodium and 2 dissociated nitrate ions on both sides, so those get canceled out. We have dissociated silver and carbonate ions on the reactant side, and undissociated silver carbonate as a solid on the right-hand side, or the product side. And actually, as you get used to doing precipitation reactions and net ionic equations, there's a general pattern that emerges, which is if you look at the 2 reactants and you figure out what the product is. So let's say you look at your silver nitrate and your sodium carbonate. You check to see what happens when you swap the cation and anion pairings, and you realize that silver carbonate is going to be your insoluble compound. The general format for the net ionic equation for a precipitation reaction is always the insoluble product, silver carbonate in this case, as a solid on the right-hand side, and that will be your only product. And the reactants are the dissociated ions that make up this compound. So silver carbonate consists of silver ions and carbonate ions. You need 2 silver ions for every 1 carbonate due to the charges. And the dissociated forms of those ions are going to be the reactants. And we need to use a 2 here to have the correct number of silver ions and an implied 1 in front of carbonate to have the correct number of carbonate ions. So as you get used to applying solubility rules, it might be possible, depending on how comfortable you are, to get the net ionic equation almost immediately based on that format.